Hello everyone, welcome back. Today we're going to talk about chapter 10. So chapter 10 is about the two sample confidence intervals. So we actually just have one section for this chapter. So that is confidence interval for the difference between two means and is for independent samples. So let's look at an example. One researcher wants to compare Conroe High School students' ACT score with that of Huntsville High School students. So now, instead of just one population, we really have two populations. So population 1 represents Conroe students' ACT score, and then the population mean we use mu1 to represent that. And we do have population 2, which is Huntsville students' ACT score, and then we use mu2 to represent the mean of that population. So to estimate the means, we need to collect sample. So we have sample 1 from this population, and another sample, we call it sample 2 from this population. So we can compute x1 bar and x2 bar separately for each population. Then we're going to say if for this study, the comparison is between the two populations. High school, the researcher wants to compare Conroe High School students' ACT score with that of Huntsville High School students. Then we actually want to look at mu1 minus mu2, which is the population mean difference. Then, based on what we learned from previous chapters, mu1 minus mu2 is a population parameter. We have to estimate that, and then we use the point estimate to estimate the population parameter. The point estimate is going to be x1 bar minus x2 bar. Then we want to have something like this, the distribution of x1 bar minus x2 bar. If we can say that's normal, then we can draw this bell-shaped distribution for x1 bar and x1 bar minus x2 bar. Then we can generate a confidence interval for that population mean difference. The assumptions to make sure x1 bar minus x2 bar follows a normal distribution will be like this. Simple random sample independent of each other, and then we have approximately normal distribution, or each sample size is larger than 30 for the original two populations, population 1 and population 2. Then the variance of x1 bar minus x2 bar are going to be the variance for the separate x1 bar and x2 bar plus together. So if we know that, we can obtain the standard deviation of x1 bar minus x2 bar, which is square root of sigma 1 squared over n1 plus sigma 2 squared over n2. So that is the standard deviation. So then we can construct a confidence interval. We say this confidence interval is when sigma 1 and sigma 2 are known. So now we still use the original population standard deviations. So when they're known, and the confidence interval going to be given, we actually can generate this ourselves, because confidence intervals formula always looks like point estimate plus or minus critical value times standard error. Then point estimate we have is x1 bar minus x2 bar, the critical value in the standard deviation of the sampling distribution. X1 bar minus x2 bar will be the standard error in this formula. So that's exactly what we have here. And then we can directly use this for questions. Let's look at this example. An experiment was planned to compare the mean recovery time in days from the common code for persons given a daily dose of vitamin C versus those who did not receive a supplement. So we actually have two populations to compare. One is no vitamin, and then one is vitamin C. And then we have the information that how large the sample size will be, and then the sample mean calculated, and then the population standard deviation known to be 2.9 and 1.2. Then we can use some stat notation to label all this information. So sample size 1, so that's N1 and N2. So that's going to be x1 bar, x2 bar. So we use 1, 2 to label different information from different populations. And population standard deviation 1, so sigma 1 equals 2.9, sigma 2 equals 1.2. So now we want to find a 95% confidence interval. We know alpha equals 1 minus 0.95 equals 0.05. And that tells the z sub alpha over 2 equals z sub 0.05 divided by 2. That's z sub 0.025. So we need to check 0.975 in the standard normal table. So 0.975. Usually we don't have an exact number, but for 0.975 we do. And then the reading for the critical value or z-score will be 1.96. So we write it down, that's 1.96. And then write down the formula again, x1 bar minus x2 bar plus or minus the critical value z alpha over 2 times square root of sigma 1 squared over n1 plus sigma 2 squared over n2. So plug in. 6.9 minus 5.8 plus or minus 1.96 times square root of 2.9 squared over 35 and plus 1.2 squared over 35. And then we can calculate the margin of error first using a calculator. So we have 1.96 times the square root of 2.9 squared divided by 35 plus 1.2 squared divided by 35. And the whole thing takes square root, that's power of half. So that's all. And then margin of error equals 1.04, 1.0397, that's 1.04. And then the point estimate is the difference of the two sample means. 6.9 minus 5.8, so that's 1.1. So what we really have is 1.1 plus or minus 1.04. So that is 1.1 minus 1.04 to 1.1 plus 1.04. So that is same to say that is from 0.06 to 2.14. So the 95, we're 95% confident that the true population mean difference is between these two numbers. That's the interpretation. Okay, let's look at some other scenarios. if we don't know the population standard deviation, which is the most common situation, we don't know that, then the standard error of x1 bar minus x2 bar will then be square root of, because we don't know those, we have to replace the population information using the sample information. And then that's the only correction. But if we don't know the population standard deviation, we still have to look at two categories. The first one is sigma 1, sigma 2 unknown, but we assume they're not, the population information are not equal of each other. In that case, we can apply the watch method, and then the formula, it will just change z sub alpha to t sub alpha over 2, because these are unknown. The population information unknown, so we're looking at a t curve instead of the z curve. Then the degree of freedom we have to define. So the rule of the degree of freedom will be smaller of n1 minus 1 or n2 minus 1. So when we assume they're not equal of each other, the population standard deviation are not equal each other, we actually have a very similar formula. That is to change z to t, like we discussed before. So same question, but now we know we have a sample standard deviation and assume sigma 1 not equal to sigma 2. Although we don't know the exact number of the population standard deviation, but we assume the relationship to be not equal of each other. And then we can write down the problem formula: x1 bar minus x2 bar plus or minus t sub alpha over 2 times square root of s1 squared over n1 plus s2 squared over n2. And then plug in the known information: x1 bar, so that's x1 bar, right? That's x2 bar, that's n1, that's n2, and then we have s1, s2. So x1 bar minus x2 bar, 6.9 minus 5.8, plus or minus. So that's t sub alpha is 0.05, right? Divided by 2, 0.025, like the previous one. And degree of freedom equals the smaller of n1 minus 1 and n2 minus 1. So n1 minus 1 is 35 minus 1, that's 34. So n1 minus 1 equals 35 minus 1, 34. n2 minus 1 equals 35 minus 1 equals 34. So we want smaller of these two numbers. So whichever smaller, we're going to use that one. So now in this case, they're the same. But if we have a 30, we're going to prefer the 30. But since they're the same, so we just put 34 here. And times square root of s1 squared, 2.9 squared over 35 plus 1.2 squared over 35. And then we just need to check this value, right? So that's 1.1 again, plus or minus 34.025. So we go to this table, 34, which will be the infinite, and 0.025, which is here, and then if we check, that's 1.96. So we put down this number, 1.96, and times square root of, we can calculate that out. Square root of 0.2814. So that's going to be 1.1 plus or minus the same calculation as before. So nothing changed actually. So that's 1.04. 1.04. So that is actually from 0.06 to 2.14. So that's the second example. And another scenario is when they're unknown but assumed equal. Then we have to pull these two sample variances together. So this is called the pooled standard deviation. And then the margin of error changed a little bit because now we don't use S1 squared. So if we look at this part, that's actually same as square root of the pooled variance over N1 plus the pooled variance over N2. So we find a pooled variance, which is a weighted variance of the two sample variances, and then we replace that in this formula. So because if they're the same, so you can actually rewrite this to the pooled variance times 1 over N1 plus 1 over N2. And then this is square root of a variance, so you can pull that out to make it like this. So the only change will be, instead of using S1 squared, S2 squared in the formula, we use the pooled variance, and that is a weighted variance between S1 and S2. And the degree of freedom equals N1 minus 1 plus N2 minus 1. Since it's a pooled variance, then the degree of freedom will be N1 minus 1 N2 minus 1 together. So simplify that, that's N1 plus N2 minus 2. Again, that is for sigma 1 and sigma 2 unknown when we assume the population standard deviation are the same. Then let's see how we can apply this formula. So again, we're going to write down N1, N2, x1 bar, x2 bar, s1, s2. Then when we assume population variance equal, and then we have this formula, but we have to calculate SP first. So the pooled standard deviation will be square root of N1 minus 1 S1 squared plus N2 minus 1 S2 squared over N1 plus N2 minus 2, which is the degree of freedom of the T distribution. So now we have square root of 34 times 2.9 squared plus 34 times 1.2 squared. And then divided by N1, so that's 35 plus 35 minus 2. So we calculate this out. Using the calculator, we have square root of this whole thing, that is 34 times 2.9 squared plus 34 times 1.2 squared. And don't forget the parentheses, because add up together and then divided by 70 minus 2, that's 68. So the whole thing take square root. Okay, so that's how we type into the calculator, and then we got 2.21, 2.22 actually, 2.219. So we just write down 2.22 as the pooled standard deviation. And then we have x1 bar minus x2 bar times T alpha over 2 df equals 68, because that's N1 plus N2, 35 plus 35, 70 minus 2, 68. And then times SP times square root of 1 over N1 plus 1 over N2. So plug in, we have 69 minus 5.8 okay, here's a typo, plus or minus. Plus or minus, the critical value is going to be t sub 0.025 because 0.05 divided by 2.025 with ZF equals 68. So if we check, this is still going to be 1.96 because 68, we look at the infinite, and then 0.025, this is called 1.96. So times 2.22 and times square root of 1 over 35 plus 1 over 35, 1 over n1 plus 1 over n2. So that's going to be 1.1 plus or minus. We plug this in. This is 1.96. Using the calculator, we got 1.96 times 2.22 times square root of what? 1 over 35 plus 1 over 35. Okay, that's the whole margin of error, 1.04, 1.04. So 1.04. And then we have 1.1 minus 1.04, 0.06. And we have 1.1 plus 1.04, 2.14. So again, is approximately. So if we look at this calculation 1.0401, that is actually different than 1.0397, but they're close. Then we're working on the same example, no matter which method we use. And again, the interpretation is going to be we're 95% confident that the true population mean difference is between 0.04 to 2.14. And one more thing to mention here is if we have a positive to positive, so this is actually an interval from positive number to positive number. So that means no matter what, your difference is going to be a positive value because it's from a positive number to positive number. So non-negative. Positive means what? So x1 bar minus x2 bar represent the point estimate of mu1 minus mu2. So that tells us your mu1 minus mu2 is a positive value for most of the time. So that tells us mu1 is more than mu2. Mu1 is more than mu2. And then if they want to compare the mean recovery time in days from the common code for person give a daily dose. So that tells us what? The time for no vitamin is more than the average time for no vitamin is more than the average time for using vitamin C. So then whether the supplement make a difference, you can tell that the claim will be the vitamin C does make some difference here because of this relationship. Okay, that's all for chapter 10, and then don't forget the worksheet 10. Worksheet 10 will be posted, and